Hello, we are from Group G and this is our mini project presentation. The title of our mini project is Image Encryption using chaotic maps and DNA addition, operation, and noise effect on it. The paper is written by Manisha Raj and Shelly Garge. It is published in American Journal of Research in Science, Technology, Engineering, and Mathematics. It is published on June-August 2014 on pages 111 and 200. Members are me, alias Safira Asri, Amiral Edran bin Idwan, Muhammad Osama Anas bin Muhammad Othman, Muhammad Sakir bin Tansi, Nadiansha bin Yunaidi, and Rosemary John. Contents for our presentation are introduction, objectives of the paper, explanation, and demonstration of the proposed technique, examples, results, and conclusion. For introduction, computer network has given a great impact transmission for digital image over internet, but also risk the security of images that had been transmission. Chaotic systems are characteristically sensitive to initial conditions. A slight change in the initial condition could have vast impact on the outcome, and chaotic systems have important properties such as a periodic sensitive dependence on initial conditions, system parameters, density of the set of periodic points, and topological transitivity.
So the objective of the paper is it will discussing about a method how to encrypt image by chaos. It proposed a new digital image encryption scheme based on the linear chaotic map and DNA addition operation in order to meet the requirements of the secure encryption. And there are 4 chaotic maps, a compare and noise effect are observed by the image.
Now let's have a look at the explanation and demonstration of the proposed technique in this paper. To give a clear idea and a better understanding, we will cover the explanation from basic theory of chaotic map, scheme for encryption and decryption of image, and encryption algorithm. Like what we've learned in cryptography, the big idea of cryptographic system is to preserve confidentiality, and this paper focuses the transmission of digital images. To do so, chaotic map is the backbone of this encryption scheme, where the goal here, just like the name chaotic, is to encrypt the image without any pattern. Now, these are the fundamental properties of chaotic map. First, deterministic, which means it can be defined by a mathematical model, such as discrete equation, to allow its usability in any application. Next, nonlinear, where we don't find direct relationship of the input and output. And finally, sensitive dependence, where a minor change in the initial will cause a massive difference in the outcomes. This 3 characteristic is very crucial for building a strong crypto. Let's dive deeper into the explanation according to this research paper. Essentially, chaotic map works by implementing position permutation and grayscale substitution to encrypt an image. The security depends on the unpredictability of the pseudorandom key stream. There are 3 chaotic maps emphasized in this paper, which are Duffing map, Tinkerbell map, and Gingerbread map. One is Duffing map, also known as Holmes map. It is a discrete time dynamical system. The Duffing map takes a point x and y n in the plane and maps it to a new point given by the equation 1 and 2 as shown here. From the equation, a and b is a constant or control parameter, where usually set to a equal 2.75 and b equal 0.2. This will eventually generate a sequence of numbers that exhibits nonlinearity. Tinkerbell map. Same like the previous one, it is a discrete time dynamical system and has 4 constant parameters a, b, c, and d. The equation used for this map is shown in equation 3 and 4. Some commonly used values are for A 0.9 and 0.3, for B negative 0.6013 and 0.6, for C is 2.0 and D 0.5 and 0.27. Gingerbread man map. As shown in equation 5, in dynamical theory, it is the chaotic 2D map. The higher dimensional maps are complex but have a larger key space and are most robust compared to 1D maps. In the next part, we will see how chaotic system combines with DNA encryption schemes for the development of a strong crypto system for image encryption.
Assalamualaikum and very good day everyone. My name is Amirul Izran and I'm going to present about encryption and decryption image using DNA-based cryptography. So DNA stands for deoxyribonucleic acid, and DNA consists of 4 nucleic acid bases called adenine denoted as A, cytosine denoted as C, guanine denoted as G, and thymine denoted as T. Next, the function of DNA is to carry information from one generation to another generation, and DNA is also used to carry and hide information. So this is applied in information storage, security, and cryptography. Now we will see about DNA encoding. So we will be mapping the digital data to the 4 nucleic acid A, C, G, and T. And next, these 4 nucleic acids we need to encode it to binary numbers information such as 00, 01, 10, and 11. Now we're moving on to DNA encryption and decryption process. After we encoded the data to its equivalent nucleic acids and binary information, we will perform the encryption process. We need to apply DNA addition using the first table for encryption, and when we want to perform the decryption process, we will apply the DNA subtraction using the second table. Now we will look at how we encode and decode using the nucleic acid. Let's say we have 150 as a data and 75 is the value of the key. And first we need to convert the data value to binary form, and we get 10, 01, 01, 10, and each binary digit we map to the equivalent nucleic acid, and we get G, C, C, and G. And after that we do the same step to the value of the key. First we need to convert its value to binary digit and the equivalent nucleic acid, and after that we get the key DNA is C, A, G, and T. After we get the DNA for the data and the key, we will perform the DNA addition to calculate the cipher data for encryption. We will add the DNA of data and key using the DNA addition table, and we get our cipher data is TCT and A. And this DNA we can convert to its binary digits and also to its integer value, which is here we get value of cipher data is 220. And final step for decryption process, we will perform DNA subtraction to decrypt the cipher data. We need to subtract the DNA of cipher data from the previous calculation, which is we get cipher data is T, C, T, and A. Now we need to subtract the DNA with the DNA of the key, and the decrypted data that we get is G, C, C, and G. And to verify the decrypted data, we will convert it to the equivalent binary digits and integer value, and we can see that we get the exact value of the data, which is 150. And that's all from me. Thank you.
To simulate the example in this paper, they use the standard 256 times 256 gray image linear as the original image. By using matchlabs of y set x1 to 0.89 and y1 to 0.29. Now set the constant parameters for each map accordingly. For the map, set for secret key power x 0 power equal to 0.89 y power y power 0 power not equal to 0.29 power a power equal to 275 and power b power equal to 0.2. Continue for Tinkerbell maps, which consist of secret key is x1 negative 0.72 y1 equal to negative 0.64 a equal to 0.9, b equal to 0.6013, c equal to 2, and d equal to 0.5. And here how the final result generate from the software. As we can see, its joystick map has different outcomes of the encrypted image. The efficiency, the robustness of encrypted image can be evaluated in few aspects, which will be emphasized further in the result. But the big ideas of it, how it can resist all kind of known attack from this encrypted image. We can see Duffing Map has performed a good encrypted image compared to Tinkerbell map and Gingerbread Man map.
Next, for the exhaustive attack, key sensitivity analysis, chaotic maps show the decrypted image and corresponding histogram with wrong secret key. Here the correct key is x0 equal to 0.7199 and the incorrect key is x0 equal to 0.7199 So we can see that the histogram of the decrypted image are fairly uniform and the decrypted image are different from the original image. So the sensitivity of the other parameters secret key is also same. And then for the statistical attack histogram analysis, the histogram shows the number of pixels for any gray value in the image. The histogram graph shows the grayscale histogram of the original image and the encrypted image of Duffing, Tinkerbell, and Gingerbread Man maps respectively. Comparing all the histogram, we find that pixel gray values of the original image are concentrated on some values, but the histogram of the encrypted image is very uniform, and that the encrypted image transmitted do not provide any suspicion to the attacker, which can strongly resist statistical attack. So, to test the correlation between two adjacent pixels in plain image and encrypted image, we can use formula of correlation coefficient where x and y are great value of two adjacent pixels in the image. For the COV-XY is covariant and for the DX is variant and EX is mean. Here, we can see the correlation between the adjacent pixel is greatly reduced. Detailed analysis is shown in table 3, which is Duffing map, and the table 4, which is Tinkerbell maps, and the table 5, Gingerbread Man map. From the result of table 3 to table 5, we find that the correlation coefficient of the adjacent pixel in encrypted image is very small. It can clearly be since our algorithm can destroy the relativity effectively. The proposed image encryption algorithm has strong ability of resisting statistical attack. Then, for the differential attack, and PCR and UACI are the two criterion that examine the effect of changing the just one pixel in the original image. The number of pixels change rate, which is NPCR, is the pixel change rate at the encrypted image or for changing a pixel at the original image, and for the unified average changing intensity, which is UACI, is the mean of this change, where E1 and E2 denote two encrypted image respectively. W and H are the width and height of image and the grayscale value of the pixel at grid ij of E1 and E2 are labeled as E1 ij or E2 ij respectively. The results are obtained by simulation for all four maps and are shown in the table 6.
In conclusion, the DNA complement and sequence additional operations totally disrupt the original image's pixel gray values. This technique provides a superior encryption effect, a bigger secret key space, and is highly sensitive to the secret key, according to the experiment results and security analysis. We compared the Duffing, Tinkerbell, Gingerbread, and 4 more chaotic maps. Duffing map performs the best as it provides the best encrypted picture and is sensitive to hidden keys. It also offers bigger key space. Noise has a negative impact on image quality, but not to the point where the image is unrecognizable.